Okay. So much fun. What question do we have?
Could I maybe take the quiz after lab? Because
Yeah, you got lab tonight, right?
Yeah, I'll probably just ask questions.
That's fine. Let's do some questions. I figure we've got some buffer lab questions.
Yes.
If you're looking for a plug, you can take this chair and plug in right under there.
Not like from the lab, but just to make sure that I'm doing this right, because it felt weird to me for some reason. Can you just show like calculating the pH at equivalence point?
Sure.
Is that still using like two different ice tables?
So calculating the pH at equivalence point. This is going to use a stoichiometry table and an ice table.
Yeah.
And like we were doing with competitive solubility, we can kind of skip the stoichiometry because at the equivalence point, the same thing is always going to happen stoichiometrically. Do you have an acid and a concentration, all that you'd like to do, or should I just make stuff up?
Actually, if you could just do the one from the report form so I can see if I got my chemistry right, that'd be cool.
Calculate the pH at equivalence point. So we have 100 milliliters of point. No, I'm going to do a different one.
Okay.
Since I'm doing it live and it's going to be videoed, I don't want to have the answer to it out in the world.
Okay.
Sorry.
You're good. That makes sense.
Right. So I'll just make up one real quick, and it'll be the exact same process. At a glance, it looked like you did the right thing.
Yeah.
Let's do.
Because it seems right at the end, but yeah.
Let's do chloroacetic acid. We'll do 225 milliliters of chloroacetic acid. So this is just acetic acid with a chlorine attached to it. So we end up with a Ka that is slightly smaller than acetic acid. Quite a bit smaller, 1.4 times 10 to the minus 3. Which you can make sense of from the structural properties, more electronegativity, more acidic. So we've got 225 milliliters of chloroacetic acid. Let's say at, what's your favorite number?
29.
0.29 molarity. Titrated with, we'll just use sodium hydroxide. What's your favorite number?
15.
0.15 molarity. Right, so this is our problem. Calculate the pH at the equivalence point. Because we're calculating the pH, we're essentially also have to calculate the volume to the equivalence point. So one, and I'm going to put both the volume to the equivalence point and the stoichiometry of this in the same problem because we're really doing the same thing. So if we look at this, we say, okay, volume to equivalence point, because of the definition of equivalence point, right? Because of that definition, we know that the moles of my weak acid, that is 0.225, let's do millimoles, 225 times 0.29, calculator help?
Yeah.
65.25. That's going to be in millimoles. That's 65.25 times 10 to the minus 3 moles. We know because of the equivalence point, we know that this MV has to be equal to this MV. This number is also going to be here. But this means we can do an M1V1 equals M2V2, not because we're doing a dilution where moles are equal, but because we're at this particular point where we define moles are equal. So do me one more favor. I'm going to ask you to do me one more favor often, but 65.25 divided by 0.15.
435 milliliters.
That is the volume to the equivalence point. Right? Now, before we move on, we should stop and say, ooh, 435, is that reasonable? Concentration is double, volume's about double. Does make sense, right? If they were the same molarities, it would be the same volume. because you'd need the same volume to get to the same number of moles. Since the concentration's about double, we need about twice as much in terms of the volume. Now let's go ahead and use that number to do our stoichiometry. And you'll see why we can kind of skip stoichiometry. So we're going to have I'm going to call it HCACT, chloroacetic acid. So this is, we'll do Cl. I don't know what to call it. Let's do this.
I'm going to call it HA. So.
What's that?
I just call it.
Let's just call it HA. Right, we can use HA. In this case, HA, we should define our shortcuts when we use it. For this problem, HA is going to be right. It's acetic acid with one of the protons replaced by a chlorine. That's what we mean when we say HA for this problem. So doing our stoichiometry, we're going to react the acid with the base. That is going to give us A minus plus the H2O. I'm not writing down the H2O. We know it makes H2O. Oh, was it 62.5, the number of moles that you calculated earlier?
65.25.
65.25. 65.25, right? We already know the millimoles of the HA here. We also know the millimoles of the OH minus because we defined them to be the same. If I take my 435 times 0.15, I better get 65.25. That's the start of my reaction. I'm going to minus 65.25. This is why we can always skip this. At the equivalence point, this is kind of a nice shortcut. At the equivalence point, all of your HA goes to A minus, and that's all you've got left. Every time we go to the equivalence point, we actually don't need to do the stoichiometry table. We just need to know that we have 65.25 moles. We just need the number of moles of weak acid we started with. Or if we were doing weak base titration, the amount of weak base we started with, right? Every time. So then we can go on to number 2. Well, that's an at sign instead of a number 2. 2. We can do the equilibrium at the equivalence point. Notice, because we've got 0 acid left, it can't be a reactant, right? We can't have water interacting with something that's not there. This means I have to do it in terms of A minus as a reactant. I don't have any HA to be a reactant. It has to be A minus plus H2O goes to HA plus OH minus. When we're in the buffer region, we get to pick which one we use at the equivalence point, or anytime we don't have both things present, we don't get to choose. I'm going to set this up as an ice table. I'm going to have my 65.25. Now notice, this is not the situation where we get to ignore volume, right? I've got zeros on the other side. I'm not going to have a ratio. I actually need the total volume here. That's going to be the 225 plus the 435. Hey, come on in. Grab a chair. We're in the middle of doing an equilibrium point calculation. So, at this point, that's going to be a molarity. What's 65.25 divided by, what is that?
It's like 0.0989.
0.0989? Can you solve that ice table? I bet you can. So that is how we do the equivalence point. Much like a lot of the things we do, as you start to notice the shortcuts, you start skipping the steps and it makes things quicker. For the equivalence point, you never really need to do the stoichiometry table. we pretty much always can just say, all my HA becomes A minus. I need to know the total volume, do the ice table.
And so then from there, though, you're going to go to POH and then you recognize POH for the pH.
Yes, notice in your equilibrium step, which I have written in green on the board, it's in terms of OH minus. So when you solve for your X, you're solving for an OH minus. You're going to use that OH minus to find your POH, convert it to H plus. Now, we know because our equilibrium is all weak base present, we know that our pH should be above 7. Let me see. I'll see if you did it right too.
Yeah.
Oh, who cares? Okay. Yeah, that looks good. Cool. So that's how we do an equivalence point calculation. And it turns out the same thought process goes to almost every point in the titration curve. It's just which shortcuts do we use depending on where we are on the titration curve.
And the choice titration is always still going to be a weak acid with a strong base.
I never said that.
I haven't even looked at homework 5, honestly. Is that
So,
always weak acid strong base? That's all we really talked about.
Yeah, but it's the same thing.
What was that question?
The question was, is the quiz on Friday is the titration just going to be a weak acid with a strong base because that's all we've done in class?
I mean, it makes sense to do the same thing. But...
And all I said was I never said that. I didn't say yes or no. I just said I never said it was gonna. I never put a restriction. I just said it was a titration problem. I will put a restriction on it. It won't be a polyprotic titration because we definitely haven't talked about that. But weak acid, strong base, they're exactly the same thing as weak base, strong acid.
Okay.
Like, there's no difference. All the calculations are the same. You just have to pay attention to whether you're doing OH minus or H3O plus. That's it.
pH at equivalence point for a weak base strong acid would be less than 7.
Yes, the pH, because if we did a weak base strong acid, you'd have weak acid as your reactant in the equilibrium. So your pH would be less than 7. Good on this? Any other questions? Okay, let's get a different question. What else do you all want to know? Yeah.
I'm confused on the lab, like finding the buffer. Like every time I plug it in, I'm not getting.
Is it because LabPal is not agreeing with you, or because you're getting weird numbers?
Right.
Okay. So, is that a good thing to talk about? How do you make a buffer?
Yeah.
Great. How do you make a buffer? Is it on the board? That's almost on the screen. I gotta leave a better buffer at the top. So we'll do it for a similar situation, right? We'll do 250 milliliters. I'm gonna make it a little different. I'm gonna do 0.2 molarity for my total. And what's a good pH for me to do? Don't give me your pH. You can give me something close to your pH.
Let's just do 5.
5. So here's what we want to do. We want to make a buffer. We want to make 250 milliliters of a buffer that has 0.2 molarity and a pH of 5. So we can think about this and it's like, wow, where do you even start? It's a buffer. What's a good equation to start with? Henderson-Hasselbalch, right? We got pH equals pKa plus log concentration of A minus over HA. So this has information that's useful in it, right? We've got our pH is 5. Since our pH is 5, we know we are going to use acetic acid with a pKa equals 4.74. How do I know that? Pardon?
Oh, you took the negative log of the.
Yeah, I just,
KA.
because I've been doing this too much, I just know the pKa's for these. I'm going to look at my target pH, which is 5, and I'm going to say which of my systems has a midpoint or a pKa close to that. Acetic acid's pretty close to that. So acetic acid works. If I looked instead at the sodium dihydrogen phosphate, you end up with a pK of 7.21, way too far away. I
So
want
for
something that's
something like that,
closer.
we would just have like a list
Yeah,
of Ka values. And then-
exactly. So for the lab, you've only got two choices. You're either close to 7 or you're close to 5. So we're doing the one where we are close to 5. So we know the pKa. Notice this is also going to give me the ratio of A minus to HA. So when I plug this all in, ooh, let's do one other trick. 0.2 molarity is going to be equal to A minus plus HA. Because that's the total concentration. It's the two things added together. We're going to have another trick we get to do with this. That's going to be nice. But this is going to allow me to substitute in one of my things. So I'm going to go ahead and replace A minus. Since I know I eventually want to know how much acid I need to add, I'm going to try to do things in terms of acid. So I'm going to go ahead and plug in all of this stuff. I'm going to have 5 equals 4.74. Why is my point up there? 0.74 plus log. A minus is going to be equal to 0.2 minus HA divided by HA. You see the substitution I did? Okay. A little bit of algebra. I'm going to do 5 minus 4.74 to the power of 10. I've gotten a little lazy with my brackets, but I think you can all follow along. I need help with calculators.
.819.
I can now solve for the concentration of acid that I want. Pretty neat, right? For you, you're going to have a couple differences. You're not going to have 0.2, you're going to have 0.1, and your target pH will probably be different. Unless you tricked me and your target pH is 5.
No.
Okay, good. I'm going to go ahead and put these brackets in while you all calculate what the concentration of HA should be.
What questions are going to be the point quiz? Like what homework questions?
Oh, it's not a homework question quiz. It's a titration quiz. So, yeah. So I'm just going to give you a problem where I've got some volume, some concentration, calculate the initial midpoint equivalence point, 1 or 2 other points at a given volume, and then 1 or 2 points of like get to the volume to this target pH.
So the homework is just more in the sense of like helping with the concepts in the lab.
Yeah, well, the homework has a couple different things that it does usefully. If you look at homework 5, there's a lot of titration problems, but they're weak-based strong acid titration problems. That'll be good for studying before the midterm. It's got a couple buffer problems. It's got a couple of conceptual problems. But we've already had a pretty good quiz on homework 4. And I was looking at the quiz that I was planning on giving next week, and it was just a titration problem anyway. So I was like, I'm just going to make a new titration problem.
I was trying to do the homework and I was looking at those.
Were you doing homework 5? Or homework? Oh, yeah. Okay. We can look at more problems from homework 4. But what's my concentration on HA?
0.07.
Yeah.
0.07.
I feel like my basic algebra
That
somehow
is lower than I was expecting.
Should I ask the concentration?
Yeah. Oh, no, that's fine. That would mean the base concentration is really high. So here's my thinking, and I could be thinking about this totally wrong, but I'm looking at this. If my HA concentration is 0.07, that means my A minus concentration, oh, it's not that far off. I just can't do math in my head. So I was looking at 0.07, I was comparing it to 0.2 and being like, that seems far off. But if we actually do it, we can use this equation to calculate A minus now. And that is going to be
0.129. Sorry, I put 0.071.
71. I'm just going to go with 0.13.
Yeah.
More details, probably good. I'm going to go with the details, 71. 129. We can back calculate now from this. We can plug these back in here and make sure that we still get a pH of 5, but I bet we will. So this is the concentrations we want. Something that's important to remember. Those are the equilibrium concentrations we want, right? Now, I'll do the ICE table real quick for how we're going to do this backwards. We're going to have HA goes to A minus plus H3O plus. We know the equilibrium values are going to be 0.071, 0.129, and 1 times 10 to the minus 5, right? Because pH of 5 would be 1 times 10 to the minus 5. I'm going to have minus x plus x plus x. I'm going to have 0. Because of the x is small approximation, that means I also know my initial concentrations, right? I'm doing this backwards, but x is small approximation still works. So this is just 0.01771, sorry, 71. And then if this is small, this is just 0.129. I don't actually need to do the ICE tables. These equilibrium concentrations are also the initial concentrations because the x is small approximation works when we're in the buffer region. So we don't actually need to do the ICE table.
How do we get 1 times 10 to the
Where did that
negative
come
5?
from? Why isn't it?
H3O plus concentration. What's our target pH?
Oh, right. Duh.
What's 10 to the power of negative 5? 10 to the negative 5. Right? So that, I know I did that pretty quick. I did that just on the slide while I was writing on the board. But I can, just because we knew what our target pH was, that's going to inform us about our H3O plus concentration. And we actually didn't need to do this table at all. The only reason I wanted to do this table is to show you x is small approximation works. Our equilibrium concentration is also the initial concentration because x is small.
Wait, and how did we get the initial concentration?
Ask that again.
How did we get the initial concentration from 0.011? You just erased it, but like the initial acid concentration.
Should have been 0.71. That was a 7. It was
Okay.
just very sloppy. Sorry. It should be these. These are the equilibriums. They're also the initial because x is small approximation works.
Gotcha.
So this is where it gets a little bit tricky. So what we want to do now is we want to do our stoichiometry. So when we look at our stoichiometry, and it turns out that, again, we're going to have a little bit of simplification. I'm going to do the stoichiometry, and then we'll think about the tricks we know to make it so we don't actually have to do the stoichiometry. If I know the initial concentrations, can you tell me my moles of acid and conjugate base at the excess point?
Yeah, because we have the volume.
We have the volume. Just do 0.25 times these to get the moles, or 250 times those to get the millimoles.
Okay.
So go ahead and tell me what's 250 times 0.071? Do you not have a calculator? Oh, okay.
17.75.
We know if we're doing this right, the OH concentration should be 0. I'm going to give myself a little bit more space here.
And that's because
If we're in the buffer region, we know that the base should still be the limiting reactant.
okay.
Right?
Mm-hmm.
What's my concentration of A minus?
32.25.
32.25. I know I start with 0 here. So what must I be adding to it if I'm going to get 32.25? I have to be adding 32.25, which means here I have to be subtracting 32.25. I have to be subtracting 32.25. And then I have to say, okay, what number must I have at the start to have so I've got 17 left over? Add those two together.
50. Okay.
And it also means I have to start with 32.25 millimoles here. Right?
Mm-hmm.
That's doing it all backwards.
Wait, where did 32.25
A minus concentration times total volume is the
right.
A minus A minus number of moles.
Why did you use A minus rather than the HA for?
We put the HA in as well.
Yeah.
But remember, we're starting with HA. We know that we started with 0 A minus.
Mm-hmm.
So we knew that 0 A minus plus some number is 32.25. So we knew the sum number had to be 32.25.
Mm-hmm.
Due to stoichiometry 1-to-1 mole ratio, we knew we had to subtract 32.25 from both of these. We knew that we wanted 17.75 millimoles left over, so I did those two numbers added together must be the total amount. There's two kind of important equations that we can kind of think about here. I just write MOS instead of moles. So one of the important things that we can realize is the moles of conjugate base at equilibrium, the 32.25, we can convert it to a concentration, but the 32.25 is equal to the moles of strong base at the start. That is to say, all of our conjugate comes from the original weak acid. That is definitely true.
Okay, and that's just in the buffer region.
Yes. If we go past the buffer region, it gets all messed up.
That should make sense. Okay.
I wish my camera was more straight on the screen, like with the board. Angles. The other thing that's important moles of weak acid at equilibrium is going to be the moles of weak acid at start minus moles of strong base at start. Right, so these two lines that I just wrote in bright orange here, they're just saying, hey, we can do stoichiometry. They're saying we can do stoichiometry, we can do it in X's small approximation, we can put this all together. And this is where the shortcut equation comes from that we were doing in class last time. So if we take these two stoichiometric facts into account, I can rewrite this thing up here as, oh, let's not do that. Let's leave it like this before we confuse things. I do want to point out one thing, though. An easier way to get the amount of acid at the start that uses this concentration. Notice it was my HA plus my A minus. Ugh, whiteboards are the worst. I've got my HA plus my A minus. I know what that is. I also know that adding the moles of those together gave me my moles at the start. I also know that I multiply my total volume to get the moles. So let's take this equation here and multiply through by 250. What's 250 times 0.2? Oops, not milliliters. Millimoles. It turns out that because all of our weak acid and conjugate base at equilibrium comes from the weak acid at the start, my total concentration gives me my starting amount of acid. Right? Because my equilibrium concentrations all come from the weak acid at the start, my total concentration gives me the weak acid I have at the start. This is because we're making a buffer through titration, it works. So you should be able to, we haven't finished. So let's think about the things we know. Things we need to know. 1, you're going to need 50 millimoles of your weak acid. If you're using 1 molar acetic acid, that means you're going to need 50 milliliters of it. If you're using the sodium dihydrogen phosphate, you've got to do a molecular weight calculation to figure out how many grams of it you're supposed to start with. 2, for this problem, you're going to want 32.25 millimoles strong base. If you're using 1 molar strong base, that's going to be 32 milliliters. And then you're also going to have to notice those volumes don't add up to 250. You're just going to add enough water to get to a total volume of 250. You're going to use nice volumetric flasks. You're going to fill right to the 250 mark, and then you're going to invert it a couple times to get it all mixed. That's how you'll make your buffer. These numbers are going to be higher than your numbers because we're using a higher total molarity. You should get numbers that are a bit lower.
So that would be the final answer then? Would be like, how do you make a buffer? And it would be you add this much weak acid, this much strong base, and this much water.
Mm-hmm.
Cool. I need to go. So I have to do my lab.
Yeah, you've got lab tonight.
I also have a 4-page paper.
Oh, man.
You're doing great. And I validate, so that's good too.
Does that take care of, who asked about making buffers? Does this
Yeah.
clear it up?
For the ratio.
So the ratio, we kind of skipped calculating the ratio, but the ratio is just this number.
Okay.
1.819 is our ratio.
Okay.
We kind of jumped past it because we were doing it on the board.
So if we're using acetic acid for a buffer system, then we would do it in we would find a volume, and if we're using the other sodium one,
You'd
then
find
we
a
would
gram. Correct.
Can I ask you a conceptual sort of question?
Yeah.
From the lab? And it's on the lab, so I don't know how much you can actually tell me, but so should like the equivalence point volumes for both 2 different weak acid titrations are close, and part of it is just saying, should it be? I didn't really understand.
So this is from the titration lab?
Yeah.
Let's take a look at this. This one I can answer directly. Why not? Because it's a good concept question.
Yeah.
Thank you.
So yeah. So we're going ahead and we are looking. So here's one of the main problems I have with whiteboards. I get this ink dust all over me. People think chalkboards are bad, but chalk just functions now. So stop. We've got how many moles of acetic acid did you have in that problem?
Or moles or the volume?
Let's do volume.
Okay, it was 15.85 milliliters that I had.
Oh, that was the amount of base to the equivalence point. Let's do 15.85 milliliters of NaOH for how many milliliters of acetic acid?
Should
be 25.
Yeah.
What was your concentration of acetic acid?
0.1589.
No, that's your concentration of base.
Yeah, okay, no, 0.10074.
10074?
Yeah.
Cool. We'll just call it 1.00. We'll call it 101.
Okay.
Should have been something close to 1. We'll call it 0.101 molarity. Okay. So we can kind of look at this and we can say, okay, 25.101, that's going to give me 2.5 if I'm doing math correctly. Approximately 2.5 moles of acetic acid. How many grams of sodium dihydrogen phosphate did you use?
0.345.
We're going to divide by the molecular weight, which is 138. If you can help me with that. Oh, I can't do that in my head.
0.0025.
Which we are calling 2.5 millimoles. So when we think about a titration, right, these numbers were supposed to be the same because that's what the lab asked us to do. When we think about the volume to equivalence point, what equation do we use? How do we deal with that? We use this idea that the moles of weak acid are equal to the moles of strong base. If they're both solutions, right? This one's a solid, so it's better. Like we have to be careful about like using those shortcuts. The real definition is just the moles of weak acid equal to moles of strong base. When we're just doing solutions, which most of the time with our acids we're doing solutions, and our titrations we're doing solutions. But this one we used a solid, so it's not just M1V1 and 2V2. Right, but the moles of weak acid are equal to the moles of strong base. Notice in both of these situations, does it matter what the weak acid is? Doesn't matter what the strong base is. It's all stoichiometry. So all that matters is the 1-to-1 mole ratio. This means these two things should have about the same equivalence point, assuming you actually got exactly that mass and exactly that volume. Didn't
Wait,
have
can you
any
just explain that
contamination.
last part again? Why does that mean that they should?
So if the moles are the same,
Oh,
the calculation is going to be the same.
right, okay.
So yeah, it makes sense that they have similar volumes to equivalence points. They're probably going to be a little off because experiments are never 100% perfect. But if we had enough time that we made you do it 30 times, I bet the average would be spot on.
Thank you.
Yeah, no worries. Hey.
So we take that one quiz. Just have it right.
Any other homework or lab questions?
Well, I guess it was just with the pKa. I know you said for the dihydrogen one, you said it was like 7.21, but like
Yes.
how did you just plug in your concentration into the log?
Not the concentration. To get.
Because you have your pH, goes log of Ka. So do I have to just look up the Ka?
Yeah, you're given it in the background.
Okay.
But you can also just use 7.21.
Okay. Yeah, I was just like.
And I forgot I need to change something on the lab. How?
Because I saw for acetic acid it was pK, but I'm pretty sure like my pH is 7.28, which is
So you're going to use the
that one.
hydrogen
Yeah.
phosphate.
Okay.
Cool. Yeah.
On homework 5, I was kind of confused on number 4. It's similar to like, I feel like what we were doing in the lab,
Uh-huh.
but we're not given a total concentration.
Let me take a look. Oh, this is, okay, so homework 5, number 4. Let's see if I can do this. I don't know if that's visible. I don't know if it's focusing. Hopefully. So homework 5, number 4. This is, oh, I'm looking at number 5 instead of number 4. What's the concentration of the base? Oh, this is not a buffer problem, actually. This is like, if you look at homework 4, it's like number 6 or something like that. Let's do it real quick, though.
Okay.
So we are asked, we've got a solution that's basic. So the pKb is given as 3.95, and the pH is given as 10.22. And we're asking what's the concentration of base at the initial. So if we set up a weak base situation, we have the base plus H2O goes to HB plus OH minus. I like to use this equation when I'm looking at weak bases. You could have done A minus plus H2O goes to HA, but I like doing this one for weak bases because it looks like NH3 going to NH4. Weak base, sorry, NH4 plus weak base conjugate acid. So I like using this one better. We're still going to end up with this situation. We're going to have Kb equals, we're going to have 0, 0 plus X plus X. Let's just leave this as concentration of B, the thing we're solving for, minus X, still going to be concentration of B, the thing we're solving for. We're going to get the same equation that we saw for weak acids with a little bit of a change. We're going to have Kb equal to X squared over the concentration of B. Remember, when we were doing this for weak acids, it was Ka equals X squared over HA. So it's really the same equation. Now, the catch is, we have to use the pKb to get our Kb, and we have to use the pH to get our OH minus concentration, which is going to be equal to X. Right? Because OH minus is all from the dissociation, then you can solve. You're going to be able to solve for the concentration, and then part B asks you to solve for a new Kb with a given concentration. Just flips it. Okay?
Okay, thank you.
Cool. I think I'm going to stop the stream because so many people took off.
Yeah.
Everyone left, so hope that was helpful. See y'all.